Hello guys, our lesson for today is boundedness of a function. The objectives of this lesson is first to understand what it is meant for a function to be bounded, to distinguish between bounded and unbounded functions, to find bounds of a function on a given interval. Boundedness of a function. Now let's talk about what it means for a function to be bounded on an interval. Let f be a function continuous from a to b on the interval ab. As you can see here in the graph, this is function f, this is the graph of function f. It is continuous on the interval from a to b. Okay, from a to b. We say that the function f is bounded if there exists two real numbers m, we call it lower bound, and m, and we call it upper bound. Such that for every value of x in AB, so for all x in AB, what happens to f of x? The function stays between these two values or two numbers. In other words, f of x is between the lower bound m and the upper bound m. Now on the graph you can see all the values of the function. No. Okay. You can see all the values of the function where x is between a and b. Every point on the blue curve is trapped between the horizontal line, these are the values of the function where x is between a and b. So trapped between the horizontal line m and m small means the lower bound and m capital means the upper bound. So the lower the function ever gets, it will stay above small m, and the higher the function reaches, it is still below m. Even though the function changes as x moves from a to b, it never goes below the lower bound and never goes above the upper bound. We are talking here if x is between a and b. So a bounded function is simply a function that stays inside a box of height between m the lower bound and m the upper bound on the whole interval. Now, by definition, a bounded function, if a function is continuous over an interval I, a, b, we say that f is bounded if there exists two real numbers, small m and capital M, such that for every real number x in this interval, we have f of x always is greater or equal to m the lower bound and less or equal to m the upper bound. Now, to understand the boundedness more, let's look at an easy example. So imagine a small roller coaster track. A car moves forward and it goes up and down, but never goes below the ground, and it never rises higher than a safety limit. These two limits act like safety walls for the coaster. So the lowest wall is the lower bound, m, and the highest wall is the upper bound, m. So no matter where the car is on the track, it always stays between these two values. Now let's look at a real function. F of x equals x squared. This is its curve, a parabola. We will study it between -2 and 2. So f of x equals x squared, where x belongs to -2, 2. Now x squared, f of x equals x squared, is a positive function. All its values are positive. So the smallest value for f of x is equal to 0, where x is 0. So if x is 0, and 0 belongs to the domain, 0 belongs to -2, 2. If x is 0, f of x is equal to 0, and this is the lowest value f can take. Now, look at the curve, the function between -2 and 2, -2 and 2. It is decreasing from -2 to 0. So the lowest value f can take is at the highest value f can take is at x equal to -2, which is f of x equals to -2 squared equals to 4. From 0 to 2, the function is increasing. So the highest value it can take is at x equals to 2, which is also equals to 4. So the function is bounded between 0 and 4 for x between -2 and 2. So a function is bounded if all its values stay between two fixed numbers. The lower bound and an upper bound. So if you look at the graph for x between -2 and 2, f of x, let's change the color, will remain between y equals 0 and y equals 4, or f of x 0 and f of x equals 4. It will be bounded between these two real numbers, 0 and 4. Unbounded function is the reverse of bounded function. We say that a function is unbounded above, sure, the function should be continuous over an interval I. The function f is unbounded above if this time for every m. For every m, there exists x in I such that f of x is always greater than m, so it has no upper bound. F of x is always greater than m. Now, what for unbounded below? Unbounded below, the continuous function over I, f, is unbounded below if, again, for every small m, there exists x in the interval I such that f of x is less than m. So it has no lower bound. F of x is always less than m for every m. So in general, we say that f is unbounded, pay attention, unbounded if it is unbounded above or unbounded below, and not and or. If it is unbounded above, we say that the function is unbounded, and if it is unbounded below, we say that the function is unbounded. If you can see the example here, over r, over minus infinity plus infinity, sure, the interval is extremely important in case of boundedness. So in the interval minus infinity plus infinity or over r, the function f of x here has no lower bound and no upper bound. It goes to negative infinity and it goes to positive infinity as x goes to minus and plus infinity. Now let's see some examples that will help us understand the concept of boundedness more. The parabola, this is the parabola. We've discussed this example from negative 2 to 2. So if x belongs to the interval minus 2, 2, then f of x is between 0 and 4. 0 for x equals 0 is included in the interval minus 2, 2. Pay attention. So f of x is between 0, this is small m, the lower bound, and 4 if x is between negative 2 and 2. This is m, it's equal to 4. So f here is bounded. What if this is the parabola f of x equals x squared? What if x belongs to r over the whole interval r? Look at the figure. As x tends to negative infinity, f of x tends to plus infinity. As x tends to plus infinity, f of x tends to plus infinity as well. So f of x tends to plus infinity as x tends to plus or minus infinity. Means f is unbounded, the same function, but the interval differs, is unbounded over r, which is, sorry, big mistake. Which is minus infinity plus infinity. Now the same function can be bounded over an interval and unbounded over another interval. Let's take the linear function, domain R, f of x equals to x plus 1 if the domain is R, over R. Over R, as x tends to negative infinity, f of x tends to negative infinity, so no lower bound. As x tends to plus infinity, f of x, which is 2x plus 1, 2 times infinity plus 1, so it's infinity, tends to plus infinity, so no upper bound as well, which means that f is unbounded. Linear functions, any non-constant linear function on R is unbounded over R. Linear functions are unbounded. Now let's move to the rational function. F of x equals 1 over x. So the rational function f of x equals 1 over x. First thing that you have to notice is that x in the denominator, so x should not be equal to 0. There is no other restrictions on this function, so the domain of definition of this function will be equal to the set R minus except 0. So let's find the limit of the function at 0. Take a look at the graph of the function here. You will see that as x tends to 0 plus, the function is not continuous. It has two curves. So as x tends to 0 plus, the function will go to plus infinity, and as x tends to 0 minus, the function tends to negative infinity. So let's write this down. So as x tends to 0 plus, f of x tends to plus infinity, and as x tends to 0 minus, f of x tends to negative infinity. Therefore, x equals 0 is a vertical asymptote for f of x. So f of x is unbounded. Now, note that even on small interval like 0, 1, at 0, the function will tend to plus infinity at 0 plus, so the function will not be bounded. So f of x is unbounded even on 0, 1 small interval. So we can say that functions can be unbounded even on a finite interval. In this example, we study an important property of trigonometric functions, whether they are bounded or unbounded. First, let us look at the function sine x. Sine x is always between -1 and 1. This means that sine never becomes too large or too small. It oscillates smoothly between -1 and 1. Therefore, we say that sine x is bounded on R. If we look at its graph, we can clearly see the behavior. The curve keeps repeating itself, as you can see, but never goes beyond 1 or below -1. So sine x is bounded between -1 and 1, bounded below and bounded above. Now, let's see the second example, tangent function, which behaves very differently. As x approaches pi by 2 plus k pi, where k in z, if x is pi by 2 plus k pi, the function increases or decreases without any bounds. It has a vertical asymptote. So the graph rises towards positive infinity on one side and falls toward negative infinity on the other side. This means that tangent x is unbounded. So, as we have said, these vertical lines correspond to what we say or what we call vertical asymptotes. So to wrap up what we have discussed before, let's look at this table. So the function x power 2 is bounded over the interval -2, 2 because it has a finite maximum and minimum, 0 minimum and 4 maximum. Now the same function, when the interval differs, it is r when the interval is r. So over r it is unbounded because the function goes to plus infinity as x goes to minus or plus infinity. 2x plus 1 is a linear function. It has linear growth. It's the equation of a line. So over r it is unbounded. 1 over x has vertical asymptote, so it is unbounded over 0, 1 and over r. Now sin x is a bounded function over r because it oscillates between -1 and 1. As a conclusion, boundedness depends not only on the function itself but also on the interval we study.